reviewers, so they can't really influence, and like we don't start. I think in 5 minutes they should be back. Okay, so is it you challenging? Okay,
yes,
please.
We would like to challenge the team from Type A to problem number. Yeah, I wanted to 12. Sound versus fire.
We'll have to reject.
Oh, okay.
Oh, this looks like
Yeah. Okay, so in that case, we would like to challenge you to problem number 8, levitating fluid.
We'll have to reject. Okay, that's 2.
Well, in that case. In that case, we would like to challenge you to problem number 16, wrist pump.
We'll have to accept. Okay, thank you very much. So we have 5 minutes preparation. You always had like okay.
Jag måste ha det 17-15 eller kursen illustrerar. I wanted to get the free jag hade scribbled out
Yeah, you can start if you're ready. Hello everyone, I'm here to present problem number 16, word pump. A word pump can be made using a tube shaped into a spiral, where it could pump water into a great height. I have to explain the phenomenon and investigate how relevant parameters affect the pumping height. So, for the geometric properties, I'll have the number of turns, pump radius, and depth in the water. For dynamic properties, which will be time dependent, it will be the angular velocity and tube diameter. And here are the contents for today. And I'll start with my setup and the two-stage phenomenon of the word pump. So here's my setup. So I have a motor and a word pump, which is a 40 centimeter diameter, where I place it inside a water tank and connect it to a vertical tube used to determine the height. So here's the phenomenon of height over time. So when I set the vertical tube height at 63 centimeters, the water will get pumped out at this height with a flow rate of 31 milliliters per minute. And it will look like this. Then, if I move the vertical tube upwards to 95 centimeters, the water will still get pumped out at this height with a lower flow rate of 18.2. But if I move the vertical tube to a very high height, the water does not reach the top of the vertical tube, so the flow rate will equal to 0. And after reaching a maximum height, we see the pump will fluctuate like that. As you can see in the height over time, it will fluctuate. So, to explain why is there a maximum height, I think there are two main reasons. First is the pump will reach its maximum pressure due to its geometric limit, like this. And the second reason is the water plug will be dripping down. And this will be time dependent, which relates to the tube diameter, which has some relation with the capillary length. So, to explain why after reaching a maximum height it will drop down, is because in this configuration, the water requires too much water head, so a pump cannot sustain it. So it actually pushes all the water back. So the water will have a flow back phenomenon, which makes the water flow into the opposite direction where we're trying to pump. And we see the water puking out from the opening. So the average flow rate for this particular pump will be 0. Then after reaching a fluctuating height, we can never reach the maximum height again. So this is due to a maximum height will be a combination of water and air. So this is less water head, so it can have a greater height. But in the full water of fluctuating height, we see it requires more water head as it will be a flow of rho GH. So that's why, however it will fluctuate, it can never go back to a maximum height again. And when it fluctuates, it will first reach a maximum water head and then go back and then keep pumping until repetition. And this repetition causes the fluctuating height out in a long time. So let's talk about the pumping process. So when a pump is rotated, it will collect water once per revolution. Then the collected water will remain at bottom due to gravity. Then the air will enter the pump. This water here forms a hydrostatic pressure. The pressure is now rho GH1. If we rotate it one more time, the second water plug forms. The pressure is now rho GH1 plus H2 due to these two stacking. Then rotate it one more time, we'll form another water plug, which the pressure is now rho GH1 plus H2 plus H3. So the role of water is to apply hydrostatic pressure, and the role of air is to accumulate such pressure in rho GH1 plus H2 plus Hn. And I also conduct a two-phase flow simulation and find the pressure will increase per turn as the air gets more compressed. This highlights the importance of the air pressure accumulating. And the key mechanism of the air and water separating is called the airlock effect. But we find in larger bond number, which is related to a diameter, will make this airlock effect fail sometimes. So the bubbling will form. And the bubbling will become significant when bond number is bigger than 10, which disrupts the pressure accumulation. Now let's talk about our quantitative model. So we consider our pump as an Archimedean spiral, which is valid due to my pump is tightly twined together. Then by setting polar coordinates and using an arc length integration on pump, we can get a mathematical form for my pump shape. Then here's the pressure evolution. To calculate pressure PI, PI minus 1 will be needed, and this will repeat. So I write down a pressure evolution recursion, accounting for a previous stack pressure. And for each evolution itself, the pressure stack will be rho GH. So I use the angles to transfer it into a height difference of a single water plug. And then we can find the pressure stack in that revolution, and we can write it here. Then I also estimated the friction loss by Darcy-Weisbach batch. It will be negligible, as it will be 2 orders below the pressure evolution. Then we can solve PV equals to constant to also obtain the length of the air plugs. Then we can finally obtain the final output pressure. So now both the air plug pressure and air plug length has been solved, where we have considered the compressibility of the air plug length with the PV equals to constant. Then, knowing the output pressure, we can solve for maximum height, accounting for airlift. So we'll derive from Boyle's law and sum up the air pocket sums to obtain the actual maximum height. Then, to summarize my model, I started with the mathematical spiral, then derived for the air plug pressure and air plug length, finally accounted for airlift. So here's how I have the simulation, and with these equations. Then I also solved for the fluctuating height range. So the fluctuation frequency will simply equal to a pump rotational frequency. But the amplitude, we can analyze it as it will go up due to positive pressure. So we can solve a half rotation to obtain the positive pressure gained in that half rotation to know the amplitude. So the modification I have is the P of n plus 1 half, which is the pressure stack in half rotation. Now let's go on to the experiments on the geometry parameters. So here are the 5 parameters I will be investigating, and I will have a quick introduction on how to read my graphs. So first, I will have a max height theory. Then we'll have a max height experiment, and a fluctuation range theory, and fluctuation range experiment. And for each data, I will run a height to time graph to determine the maximum height at the red dot and a fluctuating range in the blue arrow. So the first parameter is the number of turns. So if you increase the number of turns, the stack pressure will be rho g h1 plus h2 plus h3, as the pressure will get stacked more times. So that's why if you increase the turns, the height also increases. Then for pump radius. So if you have a pump with a bigger radius, the height difference of a single water plug will be bigger. So that's why if you increase the radius, the height difference will be bigger, causing an increase in height. Then the next parameter is the depth in the water. So when you increase the depth in the water, the length of the water plug will increase with this relation. So this is when you make the pump deeper, it will scoop up more water in a single revolution. So the plug angle phi could be interpreted as the depth of my pump in the axis here. And in lower depth conditions, there will be not enough water to add weight. And in deeper conditions, there will be not enough air to build pressure. Where we find the optimal water to air ratio will be 1 to 2, and depth to radius ratio will be 9 to 17. Now, let's analyze the dynamics of the system. So if we plot the current results, we see my theory only agrees in the hydrostatic region, but it cannot predict the increase in the height. So this is due to the water plug will disappear after some time. So if we could pump the water plug with a faster velocity, it can actually reach a greater height before disappearing. So the water distance travel will be velocity times time. And for time, we use a Taylor bubble estimation, accounting for a diameter where we can solve how long does it take for a plug to fully drip down. Then we could solve this equation, and as C is our spiral geometry constant, where we fit and find a great linear relation to the results. Then, if we look at the fluctuating height, we see an interesting increased fluctuation amplitude. This is due to a double fluctuation phenomenon we saw. So with the height to time graphs, it will have a little step here. So this is due to, in higher angular velocity, the blowback is so significant that the blowback happens with 2 revolution of blowback, right? 1 and 2. So that's why it will drop down in a 2-step motion with a very big amplitude. Then we also invest a case where very high angular velocity. So I've compared the components of centrifugal and gravity. And when we find the ratio is bigger than 1, the height significantly drops. This is due to when centrifugal force overcoming the gravity, the water will get brought up and no static pressure could form this way. Then for final parameter is our tube diameter. So we see for smaller diameter case, we see less bubbling inside the tube, so the pressure could accumulate better. And also, it will have a longer dripping time compared to the thicker one. So that's why if we have a small diameter, we can reach a greater height. Then for this data, in the larger diameter case, the bond number is around 20. So that's why we see these big bubbles forming inside. What I was able to get from this reference to estimate the water head loss, which is around 50 centimeters of water head, by these calculations and simplifications. Then if we plot the actually account for 15 centimeters loss, we see you can agree with better. Then for this green zone is our critical diameter, where we see the height got increased a lot suddenly. So this is due to, with this point, the capillary force is so strong, and the gravity is not strong enough, so it simply does not drip down. So time to disappear goes to infinite. So that's why you will get a very big bump. Now let's go on to our 3 further insights. So first is the pumping power. So this is the pumping height, and this is the flow rate. And at maximum height, very little water flow out due to a lot of water just drip down. And in lower height, all the water flow out. So what I did is times flow rate to the pumping height to obtain the pumping power. We're going to determine this region is the maximized power. Then I also investigate the case where the fluctuating height over a long time, as we see a general trend of up, down, up, down. And for a green region, it's because of the blow back position getting changed. So it will get blown back early and then transfer to blown back later. So that's why it will increase. And the opposite will happen in the red region, as it will go from blown back later to blown back early. And this will repeat, causing a general trend of up and down. Finally, for phase diagrams, this is one of my experimental graphs, and this is a height and angular velocity. So for this region, it is a height that never pumps because the water can never reach that height. And the red region is a condition where it always pumps. And the blue region is an irreversible region. As I mentioned, for the maximum height, it will be water, air, water, air, water, air. For always pump conditions, it will be all water. So this is the difference of that region. So we can never pump to this region if once the whole tube is filled with water. And we can see this happens in all of our graphs, where we can interpret all of our graphs in a 3 region of pumping. So in conclusion, the pump operates by the hydrostatic pressure stacking. And I have a recursion theory for accumulation for maximum and fluctuating height. And for the maximum height relation to regular parameters, number of turns and pump radius are close to, it is not completely linear, but it's close to linear to height. And depth in water will reach maximum at these parameters. And angular velocity, it is linear, but with some limits, as the centrifugal force cannot be too big. And the tube diameter has negative correlation. This highlights my own analytical model with the time-dependent parameters. For further insights, I've investigated the phase diagram and the pumping power and also double fluctuation. And this is the end of my report. Thank you.
Thank you. Questions from the opponents?
Yes, thank you very much. This shows that number 14. Is the amount of water that enters the pump always the same with its rotation?
Yes.
Okay, thank you. Slide 41, 42, please. What is the equation for this theory where you have the transition?
There's no theory. This is just based on experiment.
So this is just
based on experiment. Based on
experiment. Thank you. What is the maximum pipe diameter you used in your measurements?
I think it's around 1.3 diameter.
Okay. Could you please show slide number 9, where why does the slide of water is it possible to achieve the same maximum height with again after it drops?
I believe it's not possible.
Okay, thank you. Could you please show slide number 21? Yes. What process of air do you assume in your simulation? Do you assume compression? What process of air do you assume in your simulation?
Oh, no, just Boyle's law.
Okay, thank you. You assume Boyle's law. Show please slide number 5. What causes the water to fall in case of the diameter? Did you investigate a diameter that was larger than? Is that diameter of the pipe that is pumping the same as the diameter of the pipe inside of the spiral?
Oh, they are all the same.
Okay, thank you. Could you please show slide number 34? What causes these oscillations to be larger?
Because the angular velocity is so fast, so the water can travel too high, so it flows fast with a strong force.
Okay.
Okay, thank you very much. Time for preparation.
Okay, thanks. It's okay. We can turn it off. Are you It's okay. We're yeah.
Alright, let's start. Hello, ladies and gentlemen. My name is and I will show our review our opposition to problem number 16. I will start with the positive sides of the record. I will start with analyze the problem counting gave us three most important tasks. The first one is the characterization of a spiral, and this was partially fulfilled by the reporter. They consider different parameters of the cross section in the radius of the pump. However, they only focused on pipes with relatively low pipe cross section diameters. Secondly, they were to investigate the rotation, and they did indeed perform analysis on the dynamic rotation of the pump. However, we will discuss the static pump alignment in our discussion. And they performed experiment for the pumping height and allowed for and performed a simulation that achieved good accuracy with their experimental data. For the positive sides of the record, they qualitatively describe why the water pumps water upwards, and this is because of the hydrostatic pressures that are transferred by air. They consider different pipe diameters that, and for low pipe diameters, they identify that for low volume numbers, the airlock phenomenon is crucial for the transition of for the positions of water. They measured they measured the height difference in time, which allowed them for better investigation and also to capture the parameters such as the flow rate versus the water pumping height. They spotted that the pump has its geometric limits in terms of the pipe width that in case it is large, water will flow downwards. And they investigated a number of relevant parameters, such as the increasing number of turns and the depth of water, as well as the angular frequency, and to some range the tube parameter. And they prepared a simulation that allowed us for good agreement with their theory to experiments. However, they did not to any extent investigate pumps with wider kind of diameter, so the airlock phenomenon does not occur at all, and this did not mean that they did not analyze the full spectrum of possible burst pumps, and they did not analyze which pipe diameter on the wider range would allow for the highest pumping possibility. They had pumps that were rotating with different velocities, however, used the same equation for head loss without explaining the assumptions which for the Darcy-Weisbach loss, which we will want to discuss. In their simulation, they assumed that there is only the amount of water that enters the spiral with each turn is the same, which may not be necessarily true due to pressure, and their investigation of the regions for where the pumping will occur higher or when it will not was not based on any theoretical model. It was simply fitted from the experimental data based only on the observations, and also they did not change the vertical delivery pipe diameter, which is, as the problem content states, a parameter that could be investigated for the pumping height. So now I would like you to invite you to the discussion, and please show us the slide number where you develop your theoretical model. And in the meantime, I would like to ask you the question: how do you determine the amount of water that is taken by the pump in each of the turn?
Oh, it's related to depth. So like if you make the pump deeper, it will just scoop up more water because like initially it's depth. Yeah.
Okay, so do you assume that this, if you assume that the pumping amount of water that is pumped is constant, do you consider the pressure that acts on this spot, or do you just ignore that?
Which part of the pressure are you?
If you have, if I may have a marker, if you have just
Put it up.
Yes. If you have the surface of water and a pump that is in here, and it is immersed there, if there is extra pressure acting from this side, then the amount of water that stays in here should be different.
No, but
So do you include that? So I believe that you should, in your presentation, in your simulation, where if you show slide number 31, the slide where you determine the length of this.
yes,
spiral,
but
you should include the pressure that acts from this direction.
But I believe from all
good for better accuracy for theory.
yes, but I believe when the pump is rotating, the pressure does not actually push the water away. It actually push the water inside the pump to make it flow inside keep inside the spiral. So I believe the pressure does not the pressure here will be pushed over in this side. Not
Well, I disagree with you because although there is pressure, yes, that pushes the water in this direction, it changes the length of water that is taken inside, and this accumulates later in your simulation. Could you now please show the slide where you investigate the velocity of the pump into your
angular velocity.
yes, the angular velocity of rotation of your pump. Here, we can, yes, please show this graph. Here you can observe that the pumping height increases with the velocity being larger as defined by your measurements. Even though, as you said, there is drag in pipe, as you explained previously using the Darcy-Weisbach equation. So why, what causes that graph to increase?
Oh, so the reason for increase is because in most of my phenomenon, I've observed this phenomenon where the water plug drips down. So if we could pump the, actually imagine we could push the water plug with a faster velocity, just like this video I showed. It could get to a greater height before it disappears. So that's why it will increase in the maximum height.
Therefore, is it possible to achieve such high pumping height for a longer term, not just for a single short swipe of water that is pumped?
I think it's still possible because it's just the pump is just rotating so fast. So everything inside just goes so fast before everything goes back into gravity.
I agree that it's possible to achieve that pumping height for smaller numbers for short times. However, this is related to a lower flow rate. And now, please show us slide number 4, where you show your experiment. The problem content asks us to use a vertical delivery pipe. However, in your experimental setup, we can clearly see that a large part of it is not necessarily vertical. And since you model your pumping height using the positions of slacks and air between it, how does it affect the pumping height you obtain?
I actually don't think that is that important because the height will just be rho gh, and then we know even if it's like this, the height will be the same because only the actual vertical gravity causes it to.
So please show a slide where you determine the height based on the air lock inside the vertical delivery pipe. Okay. With your equation for the height based on the summing the positions of air inside of the vertical delivery pipe. This one? Yes, this one. So here we can clearly observe that you assume a vertical delivery pipe, which means that this may be a source of some sort of disagreement because the pipe is not vertical.
I think it's still possible
in your measurements.
But I think this is possible because because you could actually get this model can actually predict when a tube is tilted. So, but I just assume I have vertical because I just make the.
Well, I don't think that could be true because your model does not include the.
I removed it from the equation.
There must be some sort of. I believe you could include that. However, the problem comes and asks us to investigate the vertical.
Yeah, but only because the pipe cannot be perfectly bent 90 degrees, so I just have a little region as this kind of curve, but rest of it will be vertical.
Okay, I actually believe that you could have used a different rotary coupling that would allow you to have the pipe directly pumping to the vertical direction. This would improve the efficiency of your experimental setup. Now, please show us the slide with the bond number, where you include please show us the slide with the bond number. So what is the maximum, for what maximum width of the pipe were your experiments?
Yes, as I said, 1.3 centimeters diameter.
Okay, and did you, in your measurements, did you observe a situation where the whole amount of water fell down due to gravity and that was stronger than surface tension?
Oh yeah, it definitely happens. This is just a phenomenon I was talking about the water. Are you talking about the water plug dripping down?
Yes.
Yes. I analyzed it on a lot of.
Okay, so how would the pumping height change if the pipe diameter was larger, for example, 2 centimeters or in similar?
Yeah, I actually have a video over here. So this is the case with a larger diameter. As you can see, the whole plug dripped down very fast compared to this dripping down very slow. So I think you're talking about the effect. So
yes.
I do agree with you. If you increase the tube diameter, the height will decrease.
Yes, exactly. So I would say no. The height that you were to, I disagree with you because here you observe on your experiments that the pumping height will decrease as the number of turns grow larger. However, when the pipe diameter would be very large, you could have a spiral that obtains its optimal configurations due to the maximum height difference. And if you observe your spiral in the capillary pipe, in the pipe where the diameter is thin, you are not able to achieve the maximum height difference. So
I don't think.
I think you should, for better understanding of the effect of the diameter of the pipe, it would be desired for you to better investigate a larger range of the parameter of the pipe.
Yes, but I believe the water configuration in a pump does not depend on tube diameter. I believe.
I disagree with you because if you were to investigate a larger diameter, it would be helpful for you to maybe find this.
Yes, but the height will be very bad.
Now, please show us the slide where you investigate the effect of the Darcy-Weisbach equation where it is introduced. Does it refers to the loss of pressure of head loss in when the pipe is rotating dynamically. Did you verify whether your Reynolds number allows for the use of this equation?
I didn't. I did not apply this friction model into my experiments. I'm only just simply trying to tell you the loss it could be neglected. So the friction is not that important in this case. So I did not apply the entire thing inside.
So you did not
verify if you're asking
Reynolds number. So maybe if you did that, you would find that the friction would actually be investigated.
But I believe when the flow
model to estimate this effect.
But
more accurate.
If it's that case, you're talking about the centrifugal force. It's a lot more important than the friction.
Well, I strongly disagree with you. In your presentation, you showed that the centrifugal force for the lower pipe velocity is not so relevant. However, for larger, yes, it does prevent the pumping at all. Now, please show us the slide number 10, where you present the graph against time. So what is the, if we were to rotate the pump what is the turn of the amount of turn of this pipe that was used?
I'm sorry, we don't have time to discuss this topic. I do
okay. Thank you. So in our opposition and discussion, we were able to find that the reporter focused well investigated the case with the pipe diameter being low. However, the range of the pipe diameters they chose to investigate was too narrow to give them the very full understanding of what would happen for the large pipe diameters, and they did not. Because of that, they were not able to perform an optimization for the pumping height that they could achieve with a different number of turns. They developed a model for rotational velocity, which had good accuracy with the measurements. However, it was not the assumptions of it, such as the type of head loss, were not verified sufficiently for it to be fully physically correct, and their simulation did not include the effect of the pressure that changes the amount of water that is taken inside, which causes some misalignment.
Okay. Thank you much. Time for questions on the video.
To the reporter, did you try to change the interpipe gap? Like,
oh no, I make them tightly twined together, so that it's zero.
So you could have also explored changing the interpipe gap and its difference. Okay, and to the opponent, how do you think air bubbles obstruct the data collection in the experiment? As you told.
Well, they could affect the data collection because they confer the pressure that is generated by the vertical delivery pipe. However, the model that includes these changes attempts to fight that, but yes, this affects the pressure, which is not equal to the total pumping height.
So if I'm not wrong, you also told that the curve geometry of the pipe also affected the experiment, and this
yes, for example, if the pipe was wider, then the pumping height would grow at a lower rate.
So what's your take in his argument?
Yes, just from my experimental results, larger diameter means lower height. So that's why I didn't go further in height, because I believe that just caused a lot of bubbling, so the pressure accumulation is just failing.
So you can still try to make it more vertical and test it.
So yes, so I just think that's not important because it will just go down, and because pressure accumulation.
And also, did you also assume the radius of the pipe to be constant even after pumping water into it into a certain pressure? Because the radius of the pipe could have also exceeded a little bit as water was inserted inside.
I don't think so because I just stick it on the water pump. I make it's stable. It's not gonna change.
So it didn't change, not even a bit.
No.
Okay, that's fine. So also my another question to you is, in the experimental setup, you rotated the pipe, the first one, right? But as you rotated it, the column head should also rotate along with it, right? Like, so you have a burst pump and you are rotating it, and you have a vertical.
You're talking about the vertical pipe,
Yeah.
right?
And why didn't it rotate along with it?
So I have a I have a thing here. This little gold thing. So it's like a connection. So only this part rotates and this part don't.
Oh, so this part was constant and only the
Yeah,
pipe
this
rotated.
is set, so it will look like this.
So
The
did it
pump
have
is
any
rotating
effect
like this.
in your experimental data? Did that device or equipment have any effect in your data?
No, I don't.
Are you
think-
sure?
What?
It didn't have any effect. Okay.
I don't think we have.
May I add to that?
Yes.
Yes, I disagree. It may have if it is larger than the diameter of the pipe, as then you would not have the exact same airlock in the vertical delivery pipe, and the use of that element would allow the opponent to build actually a vertical tube as a petrol element.
As you understood. Okay. Yeah. Thank you.
Thank you very much. Time for preparation.
Okay, please start. Time is running.
You can start speaking.
Okay. So first of all, for the reporter's part, they explain the geometrical parameters well in the experiment, and they also explain the dependence on number of turns, the pump radius, and the angular velocity, and its effects in the experiment. And in the data analysis part, they also had good analysis and reasoning about the height oscillations and the bubble formations and the effect of the air bubbles inside the tube, inside the vertical. And they, but although they, what they didn't have, and they didn't have, they didn't clarify regarding the control of air bubbles in the experiment. Although they investigated its effect, in their report, and no analysis regarding deviations from the theoretical graph. This showed how much it deviated from the theoretical model, but not why it deviated from the model. And the hydrostatic pressure along the tube was also modeled really well in their presentation. And the Archimedean spiral model and stack pressure approach was quite appreciated. I quite appreciate their effort in this approach. But they told that they took PV is cost as constant in their report, and this process was not really well explained, and neither was pressure simulated well using the graphs. Although they just slightly talked about the effect of pressure in the experiments, but it was not simulated using graphical tools. And they added for the opponent part, they rightly mentioned that they added isothermal assumption and Boyle's law, that is PV is cost constant, might be inaccurate in their report. And they also stated that the air pressure changes the geometry, which later accumulates and distorts the experiment. And they should have also considered the negligible impact of the curved pipe diameter, as we discussed earlier. And they also missed the effect of coupling in the pipe to held it straight in the column, although they agreed with it later, after I mentioned. And the opponent also asked what process of air was in the simulation, and the reporter's answer was Boyle's law, that is PV was constant. And we think it is necessary for them to elaborate on this assumption. And opponent also mentioned that what causes the height oscillations to be larger, and reporter replied saying blowback angular velocity was pushing it upwards, and we agree with the reporter with this approach. And opponent also mentioned the curved geometry of the height measuring the pipe affecting the data, and reporter and said there was no effect because of the curved geometry of the pipe. But I think they should have still explore the straight approach and the deviations caused by it. And they also asked if there was a situation where all the water fell down due to gravity, and the reporter said that they did analyze it, and the bigger diameter fell faster. And they also showed the video which agreed with the assumption. And
Time is up.
And
okay. Thank you very much. 2 minutes concluding remarks. Okay, so the main how the pump works is by hydrostatic pressure stacking, and the air separates the water plug and makes the airlock effect and making all the hydrostatic pressure stack up. And I also solved the pressure by the accumulation recursive theory. And so the parameters I've solved, first is the radius and the number of turns. As we see, a pump height increases. Then for depth in the water, you see the optimal ratio will be water to air is 1 to 2, or depth to radius ratio is 9 to 17. And for angular velocity, we're able to find the pumping height increases linearly in the beginning because of the pushing from a high angular velocity is faster, but after reaching the threshold for the centrifugal force being too big, it will drop down. Then for the tube diameter, so we see the pump height increases as the diameter decreases due to the time for the plug to fully drip down. Then in the discussion and the answers to the opponent and reviewer, so I have mentioned PV equals a constant in my report on the how the modeling works, and the length of the water plug is determined by the depth. So if you make the pump deeper, it will scoop up more water in a single revolution, as I believe it will not be affected by the pressure the opponent mentioned. And also, angular velocity will increase the results due to it can push the water plug faster at a faster rate, making it go to a greater height. Then only the pressure only depends on the vertical direction, as in the rho GH. As if you make the vertical tube tilted, it will also reach the same maximum height. And for a larger diameter pipe, we see the bigger bond number, which makes the water drip down. So I think the conditions where a larger diameter tube will still decrease in the results. And for the setup, the reverse bottom, I believe the radius will not change during the pumping because I just stick it on the board and it will not move. And then there will be no rotation on the vertical tube as I set it on a frame and one side is turning and one side is not. And this is end of my concluding remarks. Thank you.
Okay, these questions from jury members.
I have a question to the reporter. You say that as the pipe diameter decreases, height will increase.
Yes.
Let's assume we can take d to goes to 0. Would it increase infinity, so is there some divergence or somewhere it would converge?
I believe if it's increased so small, the surface tension will be so strong, and I think the push from the
No
pump.
surface tension, like super fluid or something
Yes,
like that.
So you're talking about no surface tension and in a very small diameter
Yes.
tube. I think it's still. Also, but if that condition, the gravity will still be there.
Yes.
Yes. So it will still due to the pump's geometric limit, like H1, H2, H3, and that will be the maximum height, I believe.
Okay. The ratio 1 to 2, it's theoretical or empirical or like where?
It is from my experiments, but my theory
Yeah.
looks quite similar in that region. I mean,
Like,
yeah, our theory is a little bit on the right side, but yeah.
do you have any simple explanation why?
I don't think I know. Let me.
It's just like okay, so it's just like the theory tells it and.
The point I said 1 to 2 is an experiment, which is.
Oh yeah, okay, but the theory says it's like I don't know 1 point something.
Yeah.
Okay, thank you.
I might explain.
Okay.
So we would have the slugs, the slugs of water, they would constitute about half of the turn. So maximum height difference would be obtained on one side and on the other. However, this ratio would decrease if the pipe converges very fast to 0 on the spiral.
Okay, this would be 1-to-1 ratio, but
This
1
would
to
be,
2.
then it would be called, yeah, no, 1 to 2 is in the situation where the slugs are, when they convert, the spiral becomes smaller, then each slug of water will take a lower.
Okay. Patrick?
I have a question to the opponent. You mentioned in your presentation that a negative point that the reporter only investigated dynamical pump. How would you improve, let's say, why do you think that's an issue and how would you improve that point?
Well, no, I didn't say that. There was a mistake on the presentation written because they also, of course, investigated five pumps with very small rotation.
Okay. So it was just written as a
Okay, further questions? No? Everyone started up, okay. Thank you very much for everyone. So, yeah, we spare some time for the grading, so let's go for grading. Yes. But you are the last one because this is the last
think you have to do during the interview. So you are not the last one, but it's the last work. That's why you have to submit. No, you listen. But you don't actually your own time. Okay, I think we are done. Are we? No? Oh. Okay, sorry.
One more.
Okay. Grade for the reporter. 7, 8, 8, 7, 6. Grades for the opponent. No. 7, 6, 7, 7, 6. And grades for the reviewer. No. 4, 5, 5, 4, 4. Okay, that's great. We came back to being pretty equalized again. So I think the only slightly larger difference was for the report, where I was slightly lower. So my partial grades were like 3.2 and 1.3. So basically, yeah, it was a nice presentation and everything. What I liked a bit is more like, really understanding of the phenomena. Like I think it was kind of demonstrated on my question. It's like, okay, so these are experiments, this is the theory, but like why? Like, do we have any understanding? Because then, like, what would happen if we change the parameters? Like, I didn't want to ask further, but like this 1 to 2, how it would change if you use oil, if you use, I don't know, something which is heavier, something with a different surface tension, something that, some kind of understanding how the parameters will influence, because like your theory will give you a number, but like understanding what's happening and putting out the understanding of like what's happening there. And also like in the discussion, I felt like basically you probably like kind of commented and like answered all the questions and so on for to the opponent, but it was not understandable for me in a way that I would like learn and say, oh, now I understand more. Like I got all the answers, but like it didn't really help me. So I'm a bit more criticizing. Like a 6 is still a very good, figure. But I could like this could improve my feeling of the presentation. Jeremy?
I think it was a very good report. Like, I mean, you have your model, you have different experiments, and by looking at the question itself, I think you investigated a lot of relevant parameters. Yes, it could have been better, and then you will get 9 or maybe 10, but I think 8 is good for this report. Yeah.
And then
And I like how he handled the discussion as well.
Yeah. And then also,
I mean, don't forget that it's not just a report; it's also the
Yeah.
performance of the roles.
yeah, sure. No, I think that's all fine. Okay, for the opponent and reviewer, it was like as smooth as it can be. So like anyone wants to comment, so opposition review. Okay. So for the opponent.
Yeah, for the opponent, like, it's normally very difficult when you have a very good report. It makes opponent's job very difficult, but I think they've done a good job. They pointed out interesting phenomena, and they also added some value, especially with the to answers of jurors and reviewers. So well done.
Okay, and for the reviewer.
For the review, I think your questions were quite nice, and then after that it would have been an average review because of like technical difficulties. I gave a 4 and not a 5. And guys, please have the team. Like, you have a team there with 5 people. Don't let the poor guy out and try to suffer by himself to solve that issue.
Yeah, that's the basic thing, no? Like if someone is reporting and there is an issue with the computer, like then someone else from the team has to resolve the issue.
May I suggest something? Try to think about what can go wrong and discuss before the fight, what would you do if this happens? So you are ready for any kind of problem.
Okay. Any other questions, concerns, comments, whatever? Patrick?
Quick one to the opposition. Sometimes you're a bit aggressive and you ask something, he answered, you reply to that and you didn't let him react to your reply. Like, be a bit nicer sometimes.
Nicer or like let's say balanced, because
Yes.
like it's question answer comment, but it means that like you have twice, you know, like you have two shots for one
Yeah,
shot
it's
of the
exactly what Martin says.
of the other, so it's like
Yeah,
it's not a balance.
Sometimes you should have like a bigger discussion.
Yeah, like
of like
you
two,
need
three,
a
four
discussion,
points.
that's okay, but it doesn't mean that like you have to have more time. Actually, I would say still, even if you leave the discussion, more time could go to the reporter, you know, like to explain to, and then of course you can comment, but it's still the discussion on their presentation. Okay. Thank you very much. We were a bit later than I expected, but never mind. I think it was a very nice fight with very nice presentations and everything. Finally, we settled down all the technicalities. So I'm not exactly sure about the future program, but there should be dinner at Inspira at I don't